Hi everyone, Mr. Lee here. In this video, we are going to go over Newton's laws. Newton's laws. So I want to start off with Newton's third law. Okay, the third law, because this is the law that College Board likes to ask because it's not really intuitive, and even though students have an easy time reciting that law, right? If a object experiences a force, okay, there's a equal but opposite reactionary force acting on the other object. Okay, so that's the law itself, but how can we use this in terms of a multiple choice type question? All right, so let's dive into it. Let's say we have a box, right? And we say that this is box M, and we have a bigger box. Let's say this is box 12M, so it's 12 times as massive. And we were to say that when box M runs into box 12M, it creates a force F, right? So let's see, yeah. There's a force acting on 12M, so that's a force F. So if I were to create a free body diagram, so this is 12M, we would say that there's Fg, and this is the normal force, and boom, there's a force of F acting on the object. Okay, so this would be a free body diagram for the 12M object. And the question could ask, what is the free body diagram for M? All right, and so this is M, and there could be like a different amount of choices. Now, what a lot of people want to do, so first of all, we'll just say that this is Fn and f of g, so it'd probably be like Fn1, Fg1, if this is like Fn2, Fg2, right? Because there's object 1 and object 2. All right, so in this case, the answer choices could show that it would look exactly like this, okay? Because sometimes students are like, well, if it's this force on this object and it's, it has to be equal, right? They think it's going to be looking just like that, but we know that's not the case. Another way that they could show the answer choices is, let me show you here. I'll do this in red, right? So they'll be like, okay, so we have that force, and then we have this force right here, right? So they'll show these two forces, and that's not the case. So what they're trying to do here by tricking you is they're like, well, box M is exerting a force to the right, and it will feel a force of F going to the left, and that's from 12M. But remember, an object cannot exert a force on itself. Okay, it can't, and that makes this force here, that's not right. That's 100% wrong. So we'll get rid of that. And so the correct answer, of course, if you're wondering, well, what is the correct answer, Mr. Lee? It'll just be this force right here, okay? Something that looks like this. And that's because when box M is exerting a force of F to the right on box 12M, okay, and we see that with this free body diagram here, box 12M will exert a same force to the left with equal, but it's going to be going to the left, so that's the opposite. Another way that they might trick you is they could say that this is 12F because this has 12 times the mass. But remember, it is equal, okay, equal in magnitude. So in terms of numbers, it'll be like, let's say F was, I don't know, like 10 newtons. This one would also be 10 newtons instead of like 120 newtons. All right, so we can actually take this a step further. Like if there are, I don't know, 1, 2, 3, right? 1, 2, 3. So let's say this is a 1 kilogram box, a 2 kilogram box, and a 3 kilogram box. And let's say there's a force acting on the 1 kilogram box to, we'll just say to the right, of like 2 newtons. So there's a force of 2 newtons to the right. And then they'll be like, what's the free body diagram of, like, let's say object 2? Okay, so if we're taking a look at object 2, and we assume that object 1 is running into 2, and then therefore 2 is running into 3. Okay, so with that train of thought, the very first force that we should always do is the weight, and then we have the normal force, not natural as some of my students like to say, but normal force, and we have a force of 2 newtons going to the right. Okay, that's from the given, and of course object 3 exerts a force back, right? So we have this force right there, whatever that might be. All right, so like you should be able to come up with different free body diagrams from the scenario. Now, they like to take this a step further. I'm going to introduce to you the idea of elevator problems. So elevator problems come about because in a normal scenario, right, if this box were just on a regular surface, f of g would equal f of n, right? Because it's just sitting there, and we know that the net force is equal to ma, and we have f of n minus f of g equals ma. But if the acceleration is 0, we can say that f of n is equal to f of g, right? So this is one of those like given statements, okay? But what they like to do with elevator problems is they like to say that the elevator is moving. And so this is one of those things where if you can't really picture it conceptually, you might have to just like write this down and, you know, get it ingrained into your brain and memorize. When you are in an elevator, right? So let's say this is an elevator and that's my that's a rope pulling up the elevator, or like a chain. Okay, so this is Mr. Lee right there. I'm right there in the elevator. So when you're just standing in a elevator, right? And if I'm standing on a bathroom scale, remember what a bathroom scale does. The bathroom scale tells you the normal force. So in any normal or in any given situation, if you just stand on a bathroom scale, it tells you your weight because of this relationship. Okay. However, if the floor itself is moving, like in an elevator, the bathroom scale, the readings will change. Okay, so think about this through. If the elevator is accelerating upwards, that means the floor is pushing into the person. So you might notice this if you ride an elevator, that as soon as the elevator goes up, you will actually feel heavier. And that's because the floor is pushing up against the bottom of your feet. It's kind of like smushing you in. And so if that's the case and the bathroom scale is pushing against you, the scale will read higher up in weight. So for example, let's say this is our bathroom scale, right? And let's say I weigh 150 pounds. Okay, I weigh 150 pounds. Right there. And if I'm moving up in the bathroom, this 150, the needle, because the scale reads how hard the surface is pushing on me, normal force is the surface force, how hard the surface is pushing on me. If the surface is moving into me, aka moving up in an elevator, this needle will shift to the right and it'll read, I don't know, like 180 pounds. Okay, so I can actually feel that because I actually feel heavier because the floor is pushing up against me. All right, and so I'm moving up. I'm about to reach my my floor, and then when I'm about to reach my floor, the elevator slows down. Okay, so this is really cool. So with the kinematics unit, we said that whatever your velocity and your acceleration, whatever those two values are different, then that means that the object slows down. So if I'm moving up in an elevator, we can say that my velocity is positive. But if I'm slowing down, that must mean my acceleration is negative. Okay? So if I'm slowing down and my acceleration is negative, that means that the floor, okay, so the floor was moving with me going up the elevator, right? We were moving at the same rate as I'm going up, but as it's approaching the floor, the elevator is slowing down, okay? But myself, because I'm in the elevator, an object in motion stays in motion unless there's an outside force. I'm not connected to the elevator. So as the elevator is slowing down, I'm still moving with the same velocity. So what that means is even though I am moving upwards, the floor of the elevator, it's not moving as fast upwards with me. And so a really cool effect happens. The acceleration, it decreases, and because the floor is not pushing up on me as much, because the floor is like slowing down, my weight decreases. So if I weighed 150 pounds going upwards, because we're moving with constant velocity, no acceleration, no force. No force means that my normal force is my force of gravity. Okay, so as I'm going up and I'm slowing down, the floor is not pushing up against me as much. I get lighter, let's say 120 pounds. Okay, I get lighter for a brief moment, and then we get that cool feeling like in our tummy where it's like I'm going up in an elevator. It's like right, and you kind of feel like butterflies in your stomach almost. Okay. All right, so this is like elevator stuff. This is going up. Let's do the same thing, but in the reverse direction. All right, so let's say we are on the, I don't know, the 60th floor, and we're about to go down. So here we are in the elevator, and I'm on a bathroom scale. All right, so that's my bathroom. That's me on the bathroom scale, and I'm about to move down. Okay, so at that brief moment, okay, remember, you're not connected to the elevator. The elevator and you are two different systems. The elevator drops below you. Okay, it's kind of like the Tower of Terror kind of thing, right? The floor drops underneath of you. So if the floor is dropping underneath of you, the normal force, remember, the normal force is a surface force. So if the surface pulls below you just a little bit, the surface can't push on you as much. Because how can the surface push on you if it's not touching you? And so if we're looking at our bathroom scale, right, 150 pounds, and you're there, the door closes, and you're looking down at the bathroom scale and reads 150 pounds, and you push down, right? You push down. So when you push down, the elevator will start to move down. When the elevator moves down, the surface is moving away from you. So when it moves down, you get lighter for a brief moment. Let's say, I don't know, 100 pounds. All right, and then you're moving down. You and the elevator are both moving down at the same rate. Okay, so that's no acceleration, and so you go back to 150 pounds because you and the elevator are both moving down. Okay, and then you're about to reach your floor. Let's say it's the bottom floor. So we'll call that the 0th floor. Okay, the main floor. You're about to reach the main floor. Now the elevator, it has to slow down. Okay, so you're moving downwards, but the elevator has to slow down. So let's take a look into this. You are moving down, and the elevator's moving down, but the elevator has to slow down, so your acceleration is going to go up, right? Because these two signs are opposite, so that means you are slowing down. So if the elevator is accelerating upwards, but you're moving down, that means the floor is accelerating into you. The floor is pushing into you. So what this means is that the floor is pushing into you, so your normal force, boom, it increases. So let's say it's 200 pounds, right? So you feel heavier. You feel the floor pushing into you. Now this is a very important concept because this actually tells, like, they love questions like this because it's like, okay, so what's happening with your acceleration? Okay, and you just have to think about it logically, and you got to go through it logically there. And so if your weight is mg, okay, and let's say you're going up. You're going up. Now think about it. If you're going up, the floor is pushing against you, so you feel heavier. So let's say you're going up with an acceleration a. In order for you to feel heavier, normally it'll be g, but it'll be g plus whatever the acceleration of the elevator is, right? Because any number added to g will make a greater acceleration. You feel heavier. Doing this mathematically will give you a bigger weight. Right? But if, let's say, the elevator is like moving, the floor is moving away from you, right? And this is your normal weight, f of g equals mg, and the elevator floor is moving away from you, we can subtract, we can take it away from the acceleration due to gravity, because anything that goes that gets subtracted here will result in a lower weight. It's just mathematically, because you're taking away from 9.8. Okay, so keep this in mind. Very important. These elevator problems. And this actually explains, like, if you like to ride roller coasters, or there's that Tower of Terror ride, and if you're like, not for me, too scary. Well, here's another scary scenario to think about. Okay, so if you have a elevator, and all of a sudden that elevator, boom, we cut the line. Okay, so what that means is that you and the elevator are now in free fall. So free fall means that the floor is falling at the same rate that you're falling. So because the floor and you are constantly falling away from, like, you're just falling, the floor is not pushing up against you. And when that happens, well, your tummy gets really queasy. That's kind of like the drop of a roller coaster, and like you're falling. And at that moment, you become weightless. Whoa, right? You become weightless. So if you were to look at a bathroom scale, and normally, I weigh 150, but let's say we cut that elevator, that cable, this 150 will go straight to 0. You become weightless. And that's because, remember, Remember, your weight on the bathroom scale, it tells you what the normal force is. But if you're falling and the floor is falling away from you, the floor can't push against you. So you register as being weightless, and we call that free fall. Okay, so it's as if like if you're falling and we like remove the elevator from around you, it's the same thing. Okay, you're in free fall. And so let's take this into consideration. Like if, I don't know, summertime, right? We have a diving board, and you're on top of a diving board, and you boing, right? You spring up and you jump into, let's say, a pool. Okay, while you are airborne, you are considered to have, you're in free fall. So if we were to put you on a scale, the scale would read 0 newtons because the scale is also falling with you. All right, a little weird scenario there, but elevator physics, very important. Get it down. All right, what's next? One of the things that we just covered was the inclined plane, right? So if we have an object on an inclined plane, you need to know how to draw the free body diagram. One thing that they love to get students on is the idea of the normal force always pointing straight up. But remember, normal force means 90 degrees and is 90 degrees with the surface. So if this is my surface right here, this line must make a 90-degree angle with that surface. And of course, the other force is the force of gravity. And let's say there's friction, right? And let's say the object is moving up the ramp. So if the object is moving up the ramp, remember, force of friction always goes against the motion. And so I would draw it like this. Now, if the object was sliding down the ramp, you know what? I'll do it right. If the object is sliding down the ramp, instead of this force of friction right here, I'm going to do it in red. The force of friction would be like this because it's going down the ramp, right? And from there, you should be able to come up with your net force formulas. F equals ma. Remember our technique. So I'm going to get rid of this one. We have to create our new adjusted XY axes. Okay, and you have to get in the habit. You need to know how to draw these components. Now, a lot of students are like, well, how do I know? How do I know which direction the arrowheads point? How do I know this, Mr. Lee? Well, let's think about it. This force of gravity acting on this object, okay? When the force of gravity pulls on this object, in what direction will the object go? Well, if it's just being pulled, this object will move down the ramp, okay? Down the ramp, and the object will be moving to the left. All right, so that should be a dotted line. Excuse me, kind of filled it in, so I'll do dotted like this, okay? Down the ramp and to the left. That's how the object will move because the force of gravity is pulling it into the surface, right? Okay, so from here you should be able to come up with your net force formulas, okay? And you should be able to label this as either, so this one is Fyg or Fgy, and this is Fgx. Let me do that right over there. There we go. Fgy and Fgx, okay? And you need to be able to come up with the formulas. I'm not going to go into it because we did get a lot of practice in. So the kinds of problems you might see, like something like this, like how to draw the free body diagrams. Remember, without components, in free response questions, you could see this in like a multiple choice question where it's like, which one of these is the proper free body diagram? All right, so keep that in mind. Okay, another type of problem that you might see is just straight up calculations. There's not a lot of calculation type problems, but it could be like a word problem, right? If it's like, well, the normal force, let's say they give you the weight. I don't know what that weight is, but let's say they give it to you. You're like, there's a force being pushed to the right. We'll call this F1, and there's a force of friction to the left. We don't know what that is, so we'll just call it F of F, right? You need to be able to come up with the net force formula in order to determine either the acceleration or the mass of the object, depending on what other information. Chances are they'll probably give you the mass, especially if they give you the weight. So like they'll probably ask you what's the acceleration. Now this is way too easy in their eyes, and so they might like give you a little twist, right? So if this is all along the x-axis, we take a look at the x-axis along here, and we say that, all right, so there's negative f of f plus f1 max, right? and then they're like, ooh, so you should be able to turn this into mu times the normal force plus F1 equals max. And then they could ask you, what is mu? So you should be able to calculate mu, and you're able to do that if you know this value, this value, this value, this value, right? You should be able to calculate if you know all but one. But the important thing is can you come up with a net force formula? Can you go from the net force formula into based on your free body diagram, your forces, and can you substitute in the different equations, right? And once things are angled, like from before, right, the important thing here is, do you know, if this is our angle, right? If this is our angle of inclination theta, so if this is theta, that's theta, geometry rules. If you know that that's theta, what is FGX? Is that cosine or sine? You need to be able to know that. Well, so this would be FG because it's opposite. This would be sine of theta. And because this is adjacent, this is FG cosine of theta, right? You need to be able to come up with this. And because in multiple choice problems, it could give you a net force equation and be like, choose a correct net force equation for this scenario. And then you'll see one with cosines, you'll see one with sines, you'll see stuff with f of n cosine theta, and you're like, oh my gosh, which one's right? All you gotta do is know your rules, right? And know your trig rules, know how to draw the free body diagrams, and the answers will come to you. All right. So we covered the second law. We covered a little bit about the third law. Oh, with the third law, I just want to make a one last point. A classic problem. Classic problem is we have a truck. This is my truck, right? And we have a fly. Right, so when the truck and the fly, when they boom, right, when they crash into each other, the question is, which object experiences the most force, right? Is it the truck that experiences the most force, or is it the fly that experiences the most force? And a lot of students want to answer the fly because the fly gets squashed. Spoiler alert. But according to Newton's laws, both the truck and the fly, they experience the same force. Now, I'm here to tell you that I'm not going to put that question on the exam, this exact one, but there's the version, there's different versions of this kind of problem that you might come across. It could be a truck and a car, right? It doesn't have to be a fly. It could be, I don't know, a car and a ball, right? There's all sorts of different scenarios. But keep in mind, equal but opposite, right? Equal but opposite. Equal forces, but in opposite directions. That's important there. All right, so next stop in our tour is we talked about f of g, right, being the weight equation. What exactly does this mean? So if we have a very massive object versus a not so massive object, we'll say this is massive. Let's say this is 100 m's, and this is just 1 m, right? So this one is 100 times more massive than this other one. All right, so let's say we drop both objects, and they both hit the floor. Okay, and the question is, which object hits the floor first? Well, if we take a look at this equation, a lot of students want to say that because this is more massive, it'll hit the ground first. But if we take a look at this equation, there's nothing in that equation that tells us this. What the weight equation tells us is that because this is 100 times more massive, this object just has 100 times more weight. It's bigger by 100, so it'll be 100 f of g. Okay, versus this where it's just f of g. This is just a factor of 1. This is a factor of 100. So this is just 100 times. It has 100 times more weight compared to this one, and we know that because the mass for this is 100 times more massive than this one, and g right here. Okay, this is just the acceleration. Remember, acceleration does not tell you how fast something is going. That's velocity. Acceleration simply tells you the change in velocity, how much that velocity will change. And if this were here on Earth, we use 9.8 meters per second squared. Of course, for the AP exam, once again, we use 10 meters per second squared. All right, so what that means is if this was 10 meters tall, so that's about our school, which has 3 stories. Okay, so if you have a 3-story school, that's about 10 meters. I think regulation height for each room is 3 meters. So 3 times 3 is 9 plus a little bit of the extra. So that's about 10 meters. If you drop an object from the top of a 3-story building, it'll take right about 1 second to drop. Okay, but that's true for this 100 2m object versus this 1m object. They will both accelerate at the same rate. So what that means is that we are dropping both objects. So this is also key. Boom, highlight that. So important. Any object that is dropped, the initial y velocity is 0 meters per second. Okay, you gotta get that down, ingrain it into your brain. Okay, any dropped object, and we'll focus on that in a little bit, has the initial velocity of 0. And so because they both have 0 meters per second for initial velocity, and it is both accelerating at 10 meters per second squared, after 1 second, the final velocity will be 10 meters per second. Okay, for both objects, that's what this value means. After 1 second, the final velocity will be 10 meters per second for both objects. They are both traveling with the same velocity as they hit the ground. Now, if they have the same velocity, that means they are both traveling the same amount of displacement in a given time, which means that neither the 100m object nor the 1m object is moving any faster. Well, this of course is without air resistance, but they will both land on the floor at the same time. I can't emphasize this enough. They love this because students, they like the general population thinks because of cartoons and like what we experience in real life with air resistance, they just constantly think that heavier objects will hit the ground first, and that is not the case. It is just simply heavier. That's it. Okay, that is it. They will both reach the ground at the same time, as long as there's nothing in between. So what that means is, like, this is the classic scenario. Mythbusters did this. I linked the video in the classroom resources. But we have a ball dropped and we have a ball fired, right? We have a ball dropped and we have a ball fired. Now the question is which object will reach the ground first? Okay, and I think Mythbusters, they did it with a bullet. Ooh, right? And you're like, wow, bullets fall? Yeah, bullets fall because it gets affected by the acceleration due to gravity, or the force of gravity affects it. Okay, so we have a bullet that drops versus a bullet that's fired. Which bullet will hit the ground first? Well, according to the laws of our universe, both objects will fall at the same rate. Okay, which is going to be 10 meters per second squared. So if this object is falling at 10 meters per second squared and this object is falling at 10 meters per second squared, they will hit the ground at the same time. All right, now that is if and only if there's nothing in between here. Okay, there's nothing in between. So what that means is, let's say bullet fired, bullet dropped, right? So this is fired and this is just dropped. Let's say the dropped bullet, like there's like a little incline there, right? And this bullet, it falls and hits this incline because like something else was in the way. Like now this bullet has to, it has a different acceleration due to gravity because this is now AGX because it has like this angled component. Okay, so that is why only when it is in free fall. So A is 10 meters per second squared when it is in free fall. Okay, very, very, very important. I cannot emphasize that enough. All right, continuing this review train. If you ever see an object that is in equilibrium means that your a sub x, your a sub y, your a in general, they all equal 0 meters per second squared. Now this is actually very important. If your object is in equilibrium, that means it is not accelerating, it is just there. So this can come in the form of many different things. If we have an object that's sitting on a surface, equilibrium, right? There's no outside forces because we know F equals ma, and if your a is 0, 0, 0, 0, right? Your acceleration is 0. That means your net force, your outside forces, all add up to be 0. So what this could tell us, what this does not tell us is that there are no forces, because there are forces. We have the normal force there and the force of gravity here. Okay, we have two forces, but these two forces, when you add them together, they will add up to 0. Another scenario would be, this is something that we practice, hanging objects, right? Hanging objects. So if you have a hanging object like this, that means this tension and this tension and this force of gravity, when you add them all up, the net force will be 0. Well, here's a little side thing, right? Because we can't add angled forces to like forces along the x or the y. So what we did, if you remember, is we broke up these forces into its components. into its components. And so for this one, we have this tension going up and to the right. So here's my up component, and this is my right component. This tension over here is pulling up and to the left. So I have my up component, and this is my left component. Right? So we have my components. So what this tells us is, if this is my, let's say this is my ty, and this is my ty2, this is my tx, and this is my tx2. What this tells us is that if I were to add ty plus ty2 minus f of g, that net force all adds up to 0 because we are in equilibrium. This is a key buzzword. If you see this, it should red lights, warning signs, okay, think your acceleration is 0. So here's something cool. If we take a look at this equation and I were to ask you, is this rope fully supporting the weight? The answer is no, the rope itself is not fully supporting the weight. Well, one, because there's 2 ropes, but more specifically, only the vertical, the T, the Y, this Y component is holding up the weight. Okay, the Y components are holding up the weight. This angled, or this horizontal component does nothing. Does nothing for the weight. It's just holding it in place from moving from side to side. Nothing to do with the weight. The weight is only in the Y axis. Okay, so I've been talking a lot about these forces, and one of the forces that keeps on popping up is the normal force. I'm going to go over the normal force right now. If we have a regular surface, this normal force, right, and there's nothing pushing on it, this normal force is equal to the force of gravity. Right? It's the same because the force of gravity pulls the object into the surface, and the surface pushes on the object back up. All right, so let's say we have the same scenario, but we have a person pushing down on the object, F1. All right, and here we have the weight. So now, because we have a person pushing down on the object, let's say a book, and the earth is pulling on the object, so we have two things. We have two things pulling on this object downwards, or pushing on the object downwards. So what the surface has to do is it has to push back up. But this time, if we were to compare this Fn to this Fn over here to this Fn, because there's, let's say, these two are the same forces, it'll be double the amount, or we can see that with the vector. Yeah, so in this scenario, I said f of 1 is equal to f of g. So in this case, it'll be 2Fn, right? But depending on what the numbers are, it could be different. All right, now reverse. So this goes back to the elevator one as well, with how the surface was pushing. So we have f of g, and let's say you are slightly, I'll make it a little bit bigger. You are slightly pulling up. There we go. You're slightly pulling up on the object. Now you're helping. You're lifting the object off of the surface, and because you're lifting the object off of the surface doesn't have to push on the object as much. So your normal force decreases. Okay, your normal force decreases. Now the reason why the surface is even pushing back on the object is because of the third law. Remember, equal but opposite. Okay, equal magnitude, opposite direction. Equal magnitude, opposite direction. So when there's no forces acting on it, force of gravity pulls the object into the earth. Therefore, the earth will push back on the object in the opposite direction. And so here, in this third scenario, the surface doesn't push back on the object as much because you're lifting it off of the surface. So the object's not pushing on the surface as much. All right. Now that's for flat objects, but we also took a look at angled surfaces. Okay, so with angled surfaces, the normal force, remember, it's perpendicular. Okay, that's your f of n. So this is my f of g. What your normal force turns out to be is the vertical component of the gravitational force. So f of n is equal to fgy. Okay, these two forces, they are equal, assuming that there's nothing else pushing on it. And this is theta, and this is theta right here. We can say that this is fg cosine of theta. And because of this trig function, remember this is something that gives us something less than 1, that tells us that as our theta increases, okay, because of this cosine theta, as our theta increases, our f of n decreases. So this should make sense because as we get more and more inclined, right? As we get more and more inclined, as we get more and more inclined, the surface, it can't push back on the object as much because, you know, it's not really running into it as much versus like if it were flat. Okay, and so this, like the extreme case here is if this is a vertical wall. If you were to release the object would just fall, right? The surface isn't doing anything. It might as well be something like that, where the object's not even touching the surface, and that's because the surface isn't, like, there's nothing pushing the object into the surface. That's important. There's nothing pushing the object into the surface, therefore the surface does not have to push back on the object. All right. However, with this scenario here, right, if we have an object and we have a surface and you push on the object into the wall. Okay, if you push the object into the wall, so if I were to do a free body diagram, we have f of g, the wall pushes back. So we have f of g and I have, let's say, f1, that's how hard you push. The wall pushes back. This becomes a normal force, and this should make sense because here's our surface. Normal means 90 degrees. And that right there makes a 90-degree angle. So when you push an object into the wall, this is a good tie-in to our force of friction equation. Okay, force of friction equation. When you push an object into the wall, that is the only time, because we have f of n there, where the friction between the object and the wall applies. So let's talk about this friction again. All right, let's talk about friction. Remember, so if this is the force of friction equation, mu times the normal force. This right here is key. Mu, this is the coefficient of friction. There's two types. There's mu sub s and there's mu sub k. Mu sub s means static. This is when the object is not moving, and this is kinetic. That's when the object is moving. And remember, mu sub s is always greater than mu sub k. Okay, so if we were to take a look at a force of friction type problem, a couple of things that you might see. I want us to focus here, like, because chances are you're not going to be changing surfaces within problem. The thing that you are changing is normal force. So if we were to take whatever we did earlier, the normal force portion of this video, into consideration, right? So we have an object that's just sitting there, and like that's our normal force, okay? F of G, and you're like slightly pushing on it so that there's a force of friction acting on it. Okay, versus something like this where it's on a incline. Now remember what I said, if you're on an incline, your f of n decreases. Okay, so if this is f of n1 and this is your f of n2, your f of n1 is always going to be greater than your f of n2, which means that the force of friction for f of n2 is going to be smaller, right? Scenario 2 versus scenario 1. The force of friction for 1 versus the force of friction for 2, because our normal force decreases, it'll be greater in scenario 1. And so as we get more and more vertical, right? So let's see if I could create a very vertical triangle. If we get more and more vertical, oh boy. If we get more and more vertical, the more and more vertical we get, the smaller your force of friction becomes. In fact, if you have a straight up vertical wall, at that point, it's as if the wall doesn't even exist and your force of friction is 0. The only time that that changes is if you push the object into the wall, which results in a normal force. Very important idea here, okay? As your angle increases, your force of friction, it decreases, and that's because the normal force decreases. So in a scenario like this, they could ask you a couple of things, right? So if you have a box here, and let's say you push down on the box as the box is sliding left to right, the velocity is left to right, what happens with the force of friction? Well, if you're pushing down on the box, the normal force is going to increase. And if your normal force increases, your force of friction increases. Okay? Reverse scenario, instead of pushing down on the box, let's say you lift up the box ever so slightly. Okay? If you lift up the box ever so slightly, your normal force, it decreases. And if your normal force decreases, your force of friction decreases. And this should make sense because the force of friction relies on surfaces. If you are lifting the object off of the surface between the object and the surface, they're not interacting. If they're not interacting, you can't have a force of friction. The very last thing that I want to cover is the force of friction in the direction of motion. They will find ways to make this concept, which should be a really simple concept, as tricky as possible. Okay, so it's easy to imagine that if a object was just like sitting there, and this object, let's say it's sliding to the left. If the object is sliding to the left, then that means that the force of friction is towards the right. Okay, simple idea. Now, what they don't tell you sometimes is like the object is at rest, okay, and the object will move to the left, but it doesn't. Why? And then you're like, well, if it's going to move to the left but it doesn't, then that must mean that something is preventing it from moving. Therefore, there's a force of friction. And then the question will be, what direction is a force of friction? Then you think to yourself, oh, hold on. If my velocity is 0 and it's not moving, then there can't be a force of friction. But you just said that there was a force of friction. So what this means is, like, even if it's not moving, if there's a reason for it to move in a certain direction, but it's not, that means there's a force of friction acting in the opposite direction, right? So if it's moving, but like everything in the universe tells us this object should be sliding to the left, but it's not, that must mean that there's a force of friction pushing it to the right. So a way that we can view this, I feel like the trickiest kind of scenario is like if we have an object and you're pushing this object against the wall, right? If you push this object against the wall, what direction is the force of friction? Well, like you might think to yourself, there's not any force of friction, Mr. Lee, but like if we do a free body diagram, everything in this free body diagram tells us that there has to be a force of friction. One, because the problem tells you, but two, if we take a look at the force of friction equation, do we have two surfaces? Yes. Box, wall. Do we have a normal force? Yes. The wall is pushing on the object. Why? Because you're pushing the object into the wall, and therefore the wall pushes back. So you have 2 out of the 3 variables for this equation. And so if we multiply the 2, we have to have a force of friction like value. So you gotta think to yourself, all right, if there wasn't any friction, how would it move? Okay, that's the key to solving these problems. If there is 0 friction, how would it move? So if there was 0 friction, according to this free body diagram, this object will accelerate. This object will accelerate downwards, because this is the only force here. Okay, if there was no force of friction, it will accelerate downwards. That means if your initial velocity is 0, but we have a downwards acceleration, eventually it'll speed up and it'll go downwards. Okay, it'll speed up downwards. So in order to counteract this motion of downwards, the force of friction therefore has to be pointing up. Okay, so that's a little neat trick that I like to think about, is if there was no friction involved, how would it move? And just think about it that way. All right. Ladies and gentlemen, that's been my review for the dynamics unit. There's a lot to uncover there. Hopefully it was just a good review, but I did want to take the time to just go over a couple of the finer details from this unit in a review sort of form. Key thing, know how to draw your free body diagrams, know what your free body diagrams represent, and please know how to come up with your net force formula. Okay, your net force formula tells you a lot. And back to the kinematics review, your acceleration in F equals ma. Okay, that does not mean the object is moving. It just tells you the acceleration. Keep that in mind. If there is a force acting on an object, that means the velocity will change. Okay, if there's a force acting on the object, the velocity will change. Anyways, good luck, study hard, see you all next time.